In this time, we're going to be working on E, Euler's number, and natural log. These work the exact same way as when we have our regular log. The only difference is a natural log is the same thing as a log. It has a base of E. And Euler's number, this E, you can think it's about 2.718. That's approximately what it is. So you can think of this as saying, this is just the log of around 2.72. So that's all that a natural log is. It's just a log at a specific base at Euler's number. So let's look at these problems. Now, I went ahead and put the basic properties of natural logarithms. They're the same as the basic properties of logs over here, but I'm going to tell you I don't memorize them. Instead, I just remember that a log is another name for an exponent. Keep telling yourself that. So we can rewrite these without memorizing anything. If you're missing the other side of the equation, just put yourself a question mark or give it an assigned variable. So you could put a question mark there, or you could put y, whatever you like. And now let's rewrite this as a log. So we know log, our base is E, and then our exponent goes on the other side, and then our y is what we're taking the log of. Well, the log of base E is the same thing as saying ln, the natural log. So you can see here that y is equal to 2x minus y, and that's what we're solving for. So our answer will be 2x minus 1, which we could if we wanted to memorize this rule. Okay? Now let's try the next one. I always add myself a variable or a question mark on the other side. So I say log of base E, that's what our base is equal to the exponent. Okay? Well, we know log of base E is the same thing as saying ln, natural log. And we know that x to the cube root is going to be x to the 1/3. So you can see that y is equal to x to the 1/3. Let's look at the next one. So this one we're going to go the other direction. So ln is the same thing as saying log to the base E. That's another way to think of this. And you can say this is e to the 1/4 power. That's one way to think of it. Okay, so let's rewrite this. So we're going to say base E to the exponent y is equal to e to the 1/4. You can see now that y would equal 1/4. And you can also use an exponent law 3 to solve this one also. Let's keep going with just understanding that a log is another name for an exponent. So I'm going to write this as log base E Okay, let's rewrite this. So we're going to say e to the exponent is equal to 1 over e to the 5th. And this is the same thing as saying e to the negative 5. So y would be equal to negative 5. And then our last one, what's the natural log of negative 1? Well, we know this is the same thing as log base e of negative 7. We said that our log has to be greater than 0. We can never take a log of something that's less than 0. So this is undefined. Okay, moving right along. Get those calculators out and let's practice them. Okay, so I'm going to use my calculator and I'm going to evaluate this. So we want to find the E button on your calculator. Notice it's above the ln. So we're going to do seconds and then hit the ln button. It helps to have the calculator on. So let's do that again. So I'm going to say second and then the ln button. And then you can see it brings up an E. And we want to make it to be the 9/8 power. Okay, and I forgot. Let's go and stick in the very front here. I'm going to back mine up and insert 22/5. Okay, and we're going to multiply that. And we'll get 13.553. Next, we're going to do a couple transformation problems. What's so great about these problems is they work exactly like they did with our basic functions or with our log or our earlier base functions. Okay, our exponential functions are going to work the same way, whether it's an e or a number. So, state the transformation applied to the basic function. Okay, here our basic function is an e. If it's confusing, you think to yourself, that's the same thing as like a round to 2 base. Okay? Okay, so our problem says y is equal to negative e to the x minus 9. So we can see, first of all, there's a minus 9. When you have a number by itself, that's telling you up or down. So that's going to tell me to go shift down 9 from my basic function. Next, I notice that there's a negative in front of the function. When there's a negative out in front, I know it's going to be reflect across the x-axis. Now, this is identical to when we did basic functions or in the last sections where we did with a number raised to an x or a log. Same kinds of transformations. Okay, now let's consider C, the y-intercept. These are also the exact same, whether they're linear, quadratic, any kind of exponential. We know the y-intercept means that x is equal to 0. It's going to occur on the y-axis. Every point on the y-axis is an x equal to 0. So this makes us easy. What we do is we just put in an x for 0. Here I replaced my x with a 0. And I know that any base raised to the 0 goes to 1. Now be careful. The base is only the e. So this becomes 1. That'll make negative 1 minus 9. So my y-intercept will be negative 10. You can say that's 0, negative 10, or you could just say negative 10. Now my domain and my range. We just have to see what this looks like. So for this, I consider what the graph does. I just did a quick little sketch. You can see that I reflected it about the x-axis. That'd be my pink line. And then I rotated it down 9. So that would be down here at negative 10. So you can see the asymptote changed from being y is equal to 0 to y is equal to, what would that be, negative 9. Right, so it went down 9. So it was, with our basic function, y is equal to 0. So what is my domain? Well, my domain is as far left to as far right as possible. So you can see that my domain hasn't changed. It's still going to be negative infinity to positive infinity. My range has changed. The basic function range is from 0 to infinity, not including 0. Now, when I reflect it and move it down 9, now my range is going to be from negative infinity to negative 9, and it's not going to include negative 9. Let's try another one. This time, we have another Euler's number. Remember, think about like it's a round to 2, right? So we can see that we have a number out here by itself. We know that that means down 2. Okay. Shift. Now, we notice too that the x has a number with it. So when there's a number with the x, if it's a minus 5, we're going to say right 5, just like we did with basic functions. Okay? So those are going to be our transformations. It says determine the horizontal asymptote. So let's think about this. Let's do a little quickie sketch. So we can see that the horizontal asymptote has shifted from y is equal to 0 to now it's going to be going down 2. So our new horizontal asymptote will be y is equal to negative 2. Now to find the y-intercept, we know this is always the same. For the y-intercept, x is equal to 0. It's always going to be, that's the definition of a y-intercept. So we just put a 0 in for x. Okay, so we'll have e to the negative 5 minus 2. We need our calculators again. Let's turn them on. And we're going to say second, and then the ln. That gives us the e button. We're going to raise it to the -5, and then we're going to subtract 2. And I get -1.993. Now for our domain, we know that the domain is as far left to as far right as we can go. Our domain here would be -infinity to +infinity. Just like our basic function. And our range, well, our range is different now. So our range had been 0 to infinity, but now we're going to be lowering 2. So our range is going to be -2 to infinity. But just like when it's basic, we don't include that where the asymptote is. So we're going to put a parentheses. Getting good at this, so let's try another one. All right, so the transformations work the same, whether it's a basic function for those ones we learned on the very first chapters, the very first test, or whether it be the ones we learned in 6.1, 6.2, or now that we're using Euler's number or natural logs. So first, I look at the number by itself. That tells me vertical shift. And since it's a +3, we're going to say up 3. Next, we look at the expression. If there's an expression with the x, it says -6. A -6 tells me I'm going to go right 6. So now I know how my basic function is transformed. And just a reminder, your basic function is just that natural log function. Okay, so what does this look like? So you can see that I like to use the handle, right, where it crosses the x-axis. So it's going to be 1, 0. So I'm going to move it over right 6 and up 3. So now it's going to be at 7, 3. And I know my asymptote also shifts 6. So it had been an x is equal to 0, but now it's going to be at x is equal to 6. Okay, so my vertical asymptote will be x is equal to 6. Now my domain and my range, my domain of my basic function was 0 to infinity, but now I've shifted it over right 6, so my domain will now be 6 to infinity. And I know that I will not include 6 because it's an asymptote. My range was -infinity to +infinity, and you can see that my new function transform will also have the same range, -infinity to +infinity. Okay, so let's try another of these natural logs. Okay, so we have our basic function, and we want to find the transformations. So I always look first at the number by itself. A -2 tells me to go down 2. Next, I look at the expression that's with the x, and it says -6. And this one always kind of throws me, but I have to remember that -6 tells me to go right 6. Okay, and then finally, I want to look on the outside of the function, and it gives me a minus in the outside of the function. That tells me to reflect about the x-axis. Okay, let's do a quick little sketch. So we started with the black function I sketched in. That's just a typical basic function and of the natural log of x. Think of it like a regular log base e of x. It has an asymptote vertically. Our vertical asymptote is going to be x is equal to 0 at first. Okay. And then I reflected about the x-axis. You can see I made a mirror image across the x-axis. That's the pink line. And then I moved it. I moved it right 6 and down 2. And I always grab this handle right here at 1, 0. And if I moved it 6, that's going to make it 7. And if I move it down, it's going to be 7, -2. That's what I graphed down here. And then I sketched it in. Okay. So it says determine the vertical asymptote. Well, you can see that the vertical asymptote was at x is equal to 0. But when I shifted right 6, my new asymptote will be x is equal to 6. Now my domain for my original function was 0 to infinity. Now it's going to be 6 to infinity because of that vertical asymptote shift. And then my range before had been -infinity to +infinity, and it's not going to change because that won't change. Let's keep practicing these, and they're just exactly like basic quadratics, so that will help you kind of see it. So let's just try this one here. We see there's a -2. What's that tell you? Yep, down 2. And then the x plus 1, it's in the x expression. So it says +1. That's the one you have to think about really hard. That one's going to tell you to go left 1. And on the test, you can just write down to left 1. You don't have to write vertical shift down 2 and horizontal shift left 1. As long as I understand you know what direction you're going, that's fine. What's our basic function for this? Our basic function is just simply y is equal to e to the x. That's just our basic function. Okay, let's try the next one. Now this problem, the basic function is once again y is equal to e to the x. But it's been transformed because we can see there's a -3. This tells us to go down 3. We notice the x doesn't have any number with it, so just leave it alone. Doesn't move horizontally. But it does have a minus in front of it, so that tells us to reflect across the x-axis. Let's look at the next one, number 49. Our basic function here is y is equal to the ln of x, but it's been transformed. It also has a number by itself. A -8 tells us to go down 8. Next, we check our x. Our x has a -8. a -9. So since it says x -9, we know that's the wonky one we have to think about. A -9 means we're going to go right 9. And then it has a minus in the front of the ln. That tells us we're going to reflect across the x-axis. What I love about this section is if you understood it in chapter, the first test, test 1, then this will be a very easy section for you because they all work the same way, whether there be quadratics or square root or cube root or exponentials or logarithms. Our next problem is a decay and a growth problem we talked about. So let's look at problems 51 and 53. So when we're talking about continuous growth, we can use the little e, the Euler number, right? E to the k is the same thing as having our b when we talked about it in our last chapter, right? So that is what we're going to call our growth or decay factor. K, the number in front of the t, is going to be the growth or decay rate. If k is negative, then it's going to be decay. If k is positive, it's going to be growth. Okay, so let's look at problem 51. 51a says, what is the initial value? We can see clearly that the initial value is still that y-intercept. It's that a, the value in front of the exponential. So our initial value would be 782. Part B says, what is the continuous growth or decay rate? So be careful on this. The rate is the number with the t, that k. So our k is going to be 0.343, which we could give as a percent as 34.3%. And since it's positive, it's going to be growth. And then part C says, what is the growth or decay factor? So our growth or decay factor is just going to be e to the k, which in our case will be e to the 0.343. Now, you could put this into your calculator and figure it out to 2 decimals. And you can see when I do that, I get 1.41. All right, let's look at 53. This time our initial value will be 29. It's the number in front of the exponential. Our decay rate is going to be negative 0.764. So we know this is going to be 76.4% decay. And then last, we'll have e to the negative 0.764. This will be our decay factor or our growth factor. So let's use our calculator and figure that out. So I'll say second natural log and I get 0.47. Our last problem is a word problem. So I want you to make sure you do step 1, understand the problem. So pause the video and read the problem carefully. Okay, hopefully you read the problem and you understand that this is a problem. We're talking about how cars devalue. They depreciate over time. And we have a formula here, equation that's been used to model what's happening. We want to be very careful when we're reading a word problem that we understand what the variables mean. So T here represents the years after 2003, and V sub T means the value. So our first section asks us to find what is V sub 0. Realize this is not the year 0. This would be the year T after 2003 would be 0. So it's going to be in the year 2003. Put in a 0 for T, and e to the 0 becomes 1. And so our value at 2003 is going to be $25,499. Part B asks us to figure out what it will be at V sub 2. So we're going to do the exact same thing, but in place of T this time, we're going to put it 2. And we're going to use our calculator and calculate this. Put it in my calculator and I hit enter and I get 18702. So that means in 2005, because that would be 2 years after 2003, the value is 18,702. Part C asks us to use our calculator and to create a table for the values from 0 to 6. So let's just show you how to do that. So when you come in here, if you're going to make a table, you have to enter the equation into your grapher. And you can enter it in just like any function. And in place of T, I'm going to use an X. And if I want to find the table values, I'll hit second and then graph. And you can see I can have 0 through 6 right here. Next, it asks me to graph this. And let's just use our calculator and get more familiar with it. So if I wanted to graph this, I can see that my inputs are going to go from 0 to 6, but my outputs are going to go from 10,000 to around 25,500. So I changed my windows from negative 10 to 10, which is standard, to negative 1 to 10, just to give me, it's good, 0 to 6 will be well within that. And then for my Y minimum, I said 10,000, and my Y maximum, 26,000. I went ahead and changed my scale of my Y to 1,000, just so that my ticky marks will be able to see it a little easier. I'll say, oops, graph. And you can see it is exponential, and it looks like this. Now, my horizontal axis would be my years since 2003, and my vertical axis, if you labeled it, would be the value in dollars. My last part of the problem says solve numerically determine the year in which the Jeep's value drops below 73.79. So let's just use our table, since we already have it here. Oops, I can get it over there for you, and say second graph. And if I go all the way down until I'm below 73.79, you can see that when T is 8, I'm at 73.79. So anytime after that, it will be below that value. So what does that mean? When T is 8, well, T is a years after 2003. So in 2011, because that'd be 8 plus 2003, the value will be below $7,379.